sugar, going to macroscopic grains in agriculture and food industry, then to the scale of bacteria, then nanorods. If you let flowing nanorods, you can fabricate nanowires. For example, this layer has been fabricating this way, and it conducts in one direction but not in the perpendicular one. Then at the scale of viruses, and then the smallest objects are the molecules, the case of nematic liquid crystals. Of course, here I want to talk about the macroscopic grains, but interestingly, the best studied example is the case of nematic liquid crystals. So let me quickly recall what do we know for the molecular system. So here, if we apply shear flow to a nematic liquid crystal, then we observe that the average orientation of these elongated molecules is aligned this way in a shear flow, where the average orientation almost points in the direction of the flow lines, but a little bit deviates from that with an angle theta. And interestingly, this alignment angle is a material parameter. It doesn't depend on the shear rate. And then we know with, from liquid crystal studies that theta is decreasing with increasing order parameter. There we can change the order parameter by externally controlling the temperature of the system. And we also know that the viscosity of the system is reduced by about 50% due to the alignment. So we want to know what happens for the granular case. I'm going to show you three aspects: the average alignment, the rotation of the single particles in the shear flow, and the change in the effective friction due to this alignment process. So if we do the simple experiment with rice, here's a movie. I'm moving one half of my sample by moving the wall. And as you see, by the end of this movie, we'll get these tracer particles aligned just as we have seen for the case of liquid crystals. So now I want to do this experiment for a very long time and collect many data and have a good statistics. So I'm using a different cell where I rotate a plate below the material, and this way I'm shearing the sample in this dark region. This is the top view of the experiment, and as you see, the particles are sheared in this region and they get aligned. This image is already processed. We paint black all the good tracer particles which have the right shape, and of course detect their position and orientation. We used very different samples for these experiments: 3 types of rice, 2 glass rods, and then wooden rods with different aspect ratios. I don't have time to enter into all the details. You can find those in these recent papers. What I want to show first is the shear rate dependence of the average alignment angle of the particles. To measure this as a function of the shear rate, we use different rotation rates for this rotating plate. Plus, we take benefit of the fact that the shear rate is not constant in this region. So this is the angular velocity from which we can get the shear rate across the line here. And if we focus on this region here, we see that this is the radial dependence of the shear rate. So we slice up this range into 15 slices, and we collect data for each shear rate. And if we have enough data for one shear rate, then we can plot the distribution of the alignment angle of the molecules, which, as you see here, can be fitted nicely with a Gaussian. And it has an average angle which is not 0. It has also a width which is related to the ordering of this system. So we have many of these distributions. For each one, we determine the average angle, and we plot this as a function of the shear rate. And as you see here, we were able to track 3 orders of magnitude in the shear rate. And the average angle seems to be independent of shear rate, just like for the molecular case. And this is interesting because the particle-particle interactions for the granular and the molecular case are very different. For the granular case, you know we have just friction and the hardcore repulsion. But for the molecular systems, we have attractive forces like van der Waals, dipole-dipole forces. So it shows that the origin of this shear alignment is really related to the grain shape. If we go to the ordering, the order parameter again seems to be in the first approximation independent of shear rate. Maybe you can note that it slightly decreases with shear rate. So now, as we have a shear rate independent average angle, we can plot this average angle as a function of the length to width ratio of the particles. And as you see, this is nicely decreasing with length to width ratio. So longer particles are more aligned in the direction of the flow. We can also plot the same data as a function of the order parameter. We again see a decreasing tendency, just like we have had for the case of liquid crystals on my first transparency. And we can also look at what happens inside the sample, because so far I have shown data only from the surface of this material. For this, we used an X-ray tomograph in Magdeburg with Sandra Wegner and Raj Stronarius. And there, of course, we need to have a very slow flow. Actually, we go step by step and take a tomogram by this machine. It doesn't work. This is a movie which would just show how the tomograph works. So we take data from inside the sample, and we find that the bulk data are actually showing the same tendency as the surface data. The alignment angle is a little bit smaller inside the bulk, but the tendency is the same. Then our colleague also did numerical simulations with a molecular dynamics code, where he glued beads together to have elongated particles. And the red data points are now the results of these MD simulations, which are again in nice agreement with our experimental data. Kumaran and his students, Anki Reddy, and also Charlie Campbell, did simulations on a similar system with dumbbells and ellipses. And here you see their curves, which are slightly above our experimental and numerical data, but show essentially the same tendency. So far I have talked about the average orientation of the particles in the stationary state. Now if you look at a single particle, you find that in a shear flow, this single particle will rotate. And the rotation speed is not constant. It is slower when the particle is near the preferential alignment, and it's faster when it's perpendicular to it. So you see here the temporal evolution of the angles of many particles, and you notice that most of the time the particles are in this preferential range of minus 25 to 50 degrees. But then when they are out of this range, they quickly rotate. And this line, this black line, is just noting the rotation speed, which is dictated by the shear flow, by the vorticity of the shear flow. It's 1 radians per unit deformation. And you see that you often find particles which rotate with that maximum speed. And you can plot the distribution of the particle rotation speed, which is shown here for 1 material. And you can take the average of this distribution and plot it. And here we have this for different materials obtained by different methods, optically, X-ray, and the DEM calculations. And we can compare it to the old result, which is almost 100 years old, by Jeffrey, where he calculated the rotation of an ellipsoid, a hard ellipsoid, which is placed into a fluid which is sheared. And there you see that many features of these curves are similar. I would like to point out that the velocity contrast, which is just the maximum ratio of the maximum velocity and minimum velocity. So the maximum velocity is obtained when the particle is like this, and then it slows down. The minimum velocity is obtained here. So for longer particles, we have a larger difference between the maximum and minimum velocity than for shorter particles. And this is the same for the Jeffrey solutions and our experimental data. So now let me go to the transient. If you start from a random initial configuration, then you can detect how fast your system arrives to this shear-aligned configuration. So here I'm plotting the distribution of the angles, which is random at the beginning, and then evolves to this distribution, which is shown here in the right. So if we make a cut here, we'll get this one. And as you see, the system quickly goes into this shear-aligned case. In terms of deformation, this is about 1 or 2, which means that the neighboring layers need to pass 1 or 2 particles, and then the system is already aligned. The second thing which we have measured during this transient is how hard the system needs to be moved in order to maintain a constant rotation rate. So we measured the torque needed to maintain this constant rotation rate, and we plot this torque as a function of the deformation in the sample. And we see that this torque decreases. So we have the maximum torque at the beginning of the process, and we can plot the ratio of the maximum and the stationary torque, which is about 1.5 for each material, meaning that it's harder. It's about 1.5 harder to shear an unaligned sample compared to the case of the shear-aligned sample. We can also fit an exponential decay to these curves and see that the characteristic deformation needed to get to the stationary torque case is increasing with length to width ratio. So with this, I came to my summary. I want to emphasize again the main take-home messages. First, that in the stationary state, we can determine the average orientation of these particles, which seems to be shear rate independent, just like for the molecular case. But it decreases with the particle length to width ratio, meaning that longer particles are more in the direction of the streamlines. And that for the transient, we find that from a random configuration, this system evolves very, very quickly towards this shear-aligned case. You need to have only 1 or 2 unit deformations to be shear-aligned. And that during this transient, the effective friction of the material decreases. It was about 1.5 times harder to rotate the unaligned sample compared to the case of the shear-aligned sample. I would like to thank once more to my collaborators and for the financial support. And before finishing, I would like to draw your attention to our recent review paper, which just came out last week in Soft Matter, which summarizes recent knowledge about packing, dense flows, shaken system, granular gases with elongated or flattened particles. So with this, I can keep it up. Thank you.
Where the angle is not a function of shear rate, but is it a function then of your packing fraction?
We were completely dense, so we didn't change the packing fraction. That would be a very nice extension of this.
Yes, I'm asking because what would then is the mechanism by which they align? Is it because at the dense regime they don't have the rotational diffusivity anymore, so that they have to align? And if you allow for more freedom, perhaps you will have that will change.
Yes, it's not easy to control the density in this quasi-static or slow flows, but maybe in a shaken system we could do something. We didn't do this yet.
Sure.
I'm intrigued by your comparison with the Jeffreys orbits, because my recollection is that they involve single particles and that they are the dynamics in case there's a collision will change. So why compare with Jeffreys orbits? And
we just looked up what those calculations give, and there were similarities. So I thought it's worth mentioning. But of course there are also differences.
During those orbits, do you see correlation with the neighbors particles?
We tried to look for correlations, but it's not conclusive yet.
That's something we observe in soil mechanics. So in soil mechanics, we do like a lateral vertical loading, trying to shield sample with controlling confining pressure. So general observation is if we shield the sample, if we load the sample vertically, we actually observe the particle tend to be normal to the principal stress direction. But in that very localized shear band regime, the particle tend to be aligned with like a very concentrated higher shear gradient in that localized regime. So it's quite interesting result to see, but I think it's probably your observation say is not exactly the same as shear rate direction, is because the particle has another tendency to try to align to the major principal shear stress direction. So it could be a combination of these two mechanisms there. We can discuss a little bit later if you're
Okay,
interested.
yes, I'll be interested.
Any more questions? So let's thank Thomas again.